Alright, for this video, we're going to be looking at momentum concept questions to kind of check if you guys understand the basic concepts of linear momentum. So we're going to look through these. So for the first question, let's look at two identical automobiles have the same speed, but one is traveling east and one is traveling west. Do these cars have the same momentum? The answer is no, they do not have the same momentum because momentum is a vector, meaning it has magnitude and direction. For something to have the same momentum as another object, they need to have the same magnitude momentum and the same direction momentum. So number two. In Times Square in New York City, people celebrate on New Year's Eve. Some just stand around, but many move about randomly. Considering a group consisting of all these people, approximately what is the total linear momentum of this group at any given instant? Well, it would be about 0 because if we include everything in the system, in order for someone to move forward, they have to push off the ground and make something move back. Everything needs an equal but opposite reaction. So at the end, the total momentum of that system, which we assume at some point they were all standing still or came in standing still, and just started our initial position at a point where everyone was relatively still, then the total momentum would be about 0 at any given point. For number three, two objects have the same momentum. The velocities of these objects necessarily have the same direction. Alright, for part A, they need to have the same direction, yes, because momentum is a vector that's equal to the mass times the velocity vector. If two objects have the same momentum, that means their velocity must be pointing in the same direction, because in the equation, the thing that determines the direction of the momentum is the velocity. Momentum always points in the same direction of the velocity. And if they have the same momentum, the velocity has to point in the same direction. Now, when we look at the same magnitude, the answer is actually no. They don't have to have, the velocity doesn't have to have the same magnitude, because the objects might have different masses. So one object might be bigger, which means it needs less velocity to match the momentum of the smaller object that needs to be moving faster to have the same momentum. So they don't have to have the same magnitude velocities, but they do have to be pointing in the same direction. Alright, for number four, can a single object have a kinetic energy but no momentum? Now, if an object has kinetic energy, that means it's moving. That means its momentum cannot be 0, because that, unless it has no mass, but then it wouldn't have kinetic energy. So the answer is, gave away all the answers for a brief moment, but the answer is no. For part B, can a group of two or more objects have a total kinetic energy that is not 0, but have a total momentum that is 0? The answer for that one is yes. Since kinetic energy is always positive, two objects having the exact same mass, moving in the exact same speed but in opposite directions, will still have positive kinetic energy. But since momentum is based on direction, one will have a positive momentum, one will have a negative momentum, and they have the potential to cancel each other out. One object's kinetic energy cannot cancel out another object's kinetic energy, but one object's momentum can cancel out another object's momentum, giving them a total momentum of 0. So can a group of two or more objects have a total kinetic energy that is not 0, but a total momentum that is 0? Yes. Number 5, suppose you are standing on the edge of a dock and jump straight down. If you land on sand, your stopping time is much shorter than if you land on water. You're using your impulse momentum theorem as a guide. Determine which of the following statement is correct. In bringing you to a halt, the sand exerts a greater impulse on you than does the water. The answer for that one is no. Impulse is equal to the change of momentum. The initial momentum for the guy landing on the ground and landing on the water is the same. They're going to hit the ground and the water at the same velocity, so they're going to have the same initial momentum, and the water is going to eventually make them stop just like the ground is, so they're going to have the same final momentum. So they're going to experience the same change of momentum, so they are going to experience the same impulse. So letter A is false. For part B, in bringing you to a halt, the sand and the water exert the same impulse. That statement so far is true because of what we talked about in part A, but the sand exerts a greater average force. Now, the answer for that one is yes. Remember, the average force is equal to the change of momentum over time. They're both exerting the same change of momentum, but the ground is doing it much, much, much faster, meaning your time is a slower, much smaller value. You're doing it in a much smaller amount of time, so the average force exerted on the ground is greater. The water takes a while to slow you down because it's exerting a smaller average force. For part C, so part C is true. For number 6, an airplane is flying horizontally with a constant momentum during a time interval of delta t. Is there a net impulse acting on the plane during this time? Use the impulse momentum theorem to guide your thinking. The impulse momentum theorem says that impulse is equal to force times time. And also, since impulse is your change of momentum, since you have a constant momentum, you don't have a change in momentum. A constant momentum means your change of momentum is 0, which means you don't have an impulse. So the answer is no. And then for part B, there is no impulse. For part B, it says in the horizontal direction, both the thrust generated by the engines and air resistance act on the plane. Consider your answer to part A. How is the impulse of the thrust related in magnitude and direction to the impulse of the force due to the air resistance? Since the airplane is moving with a constant momentum, that means its velocity is relatively constant. It has to have a relatively constant velocity, which means that the forces acting on the plane have to be pointing in the opposite direction, so your net force has to be 0. So the impulse of the thrust related to the impulse of the force due to the air resistance, they're going to be the same, have the same magnitude, but be in opposite directions. All right, let's look at the next set of concept questions. As an object slides along the surface of the Earth, an object slides along the surface of the Earth and slows down because of kinetic friction. If the object alone is considered as the system, the kinetic frictional force must be identified as an external force that, according to the equation, decreases the momentum of the system. If both the object and the Earth are considered to be the system, is the force of kinetic friction still an external force? So basically they're saying if you have a box and the box is in itself considered the system and there's a frictional force that stops and slows down the box, the frictional force, if both the objects and the Earth are considered to be, the frictional force is an external force. The frictional force is an external force, and we can tell it's an external force because the total momentum of the system is changing. If the system is the box is moving, it has momentum, and then the box is eventually going to stop. So the total momentum is going to be 0. But the reason that the conservation of momentum didn't hold true was because it was acted on by an outside force. Now, if you take the whole Earth into account, as the momentum of the box is changing, the ground is also changing. And as the one object loses momentum, another object gains momentum. So if we look at everything on the Earth, then the frictional force is not considered an external force because it's being taken into account. So for part A, if both the objects and the Earth are considered to be the system, is the force of kinetic friction still an external force? The answer is no, because the total momentum of the Earth would not change. One object gains, one object loses, but the total still stays the same. For part B, can the frictional force change the total linear momentum of the two-body system? So can the frictional force change the two linear momentum of the two-body system? The answer is also no. And that's because its conservation of momentum holds true because all the forces are internal forces. There's no external force because the friction is inside it. So the total momentum should not change. The box may lose momentum, but then the Earth's going to gain that same momentum. So everything ends up balancing out. All right. So for question number 8. A satellite explodes in outer space far from any other body, sending thousands of pieces in all directions. Is the linear momentum of the satellite before the explosion less than, equal to, or greater than the total linear momentum of all the pieces after the explosion? The answer is it's equal to. It's like the problem we did before. The explosion caused everything to move, but in order to make one object move to the right in space, another object has to move to the left with the same momentum. So since the object started off as a whole thing, just kind of standing still in space, having a total momentum of 0, then when it explodes and you look at all the individual pieces, it should also end up to be the same as before it exploded. This is actually how they find like all this crazy dark matter, and there's all these particles in the universe that we can't even see but we know exist. And the way these scientists found out that they existed is because they did an example of these. They would look at the total momentum of the star right before, and they would look at this exploding star and then take the momentum of all the pieces missing, but that went on moving in different directions. But when they tried to calculate the total change in momentum, they found out that there was a change in the momentum. They couldn't figure out why. And then the only logical thing, or the only reason they could find, was that there are other things that are moving away from the star that we can't see or detect, that's accounting for that missing momentum. And then they, through calculations and other things way beyond my pay scale, they were able to kind of theorize what these objects were, and many of them are being discovered right now with the technology advantage. And it was based on the fact that the conservation of momentum had to hold true, and what was happening is there were some other things going on that they couldn't see and therefore couldn't calculate, but do exist. Anyways, that's farther than we need to be. Back to the questions. On number 9, on a distant asteroid, a large catapult is used to throw chunks of stone into space. Could such a device be used as a propulsion system to move the asteroid closer to Earth? The answer for that one is yes. If you just were on an asteroid and you just started chucking pieces of the asteroid away from the asteroid, you would be giving it some kind of positive momentum for the object, which means there would be some kind of negative momentum pushing the asteroid in the other direction. You could pretty much kind of try to do this. Maybe if you were like on a really, really, really icy lake, you can just imagine someone just throwing stuff out of their pockets, and it would actually cause them to start sliding more and more to the left. Okay. So for this one, we have 2 balls collide in one-dimensional elastic collision. The 2 balls constitute a system, and the next external force acting on them is 0. The table shows 4 possible set of values for the initial and final momentum of the 2 balls, as well as their initial and final kinetic energies. Only one set of values could be correct. Which set is it? The first thing we need to take into account is that they're telling us that it is an elastic collision. Elastic collisions means that the total change in kinetic energy is 0, meaning the total kinetic energy you started off with is equal to the total kinetic energy you ended with. So we look through them. So that pretty much eliminates a good chunk of these. So if we look at the total kinetic energy initially for ball 1 and 2 for part A, we find that the total kinetic energy is 17 and the total final kinetic energy is 17. So this is the kinetic energy part holds true. For part B, the total initial kinetic energy is 30, but the final is 33. So that means part B cannot be considered an elastic collision. For part C, we have a total of 43 in the beginning and 40 at the end. Again, that's not an elastic collision, cancels it out. And for the part D, we have 40 initially and 40 in the final. So we have 2 options right now that might be true, A and D. To help eliminate them, we have to use the second rule. Well, this is the rule that applies for all collisions. All collisions, that have no external force acting on them, must have a total change of momentum equal to 0, meaning momentum must be conserved. So the total final momentum has to equal the total initial momentum. So if we look at part A and find the total momentum at the beginning, we find that the total momentum in the beginning is 1, but the total momentum at the end is -6. So that's not even an actual realistic collision. There's got to be an external force acting on it. Either way, it's not an elastic collision. It's not any collision that includes that we talked about. And then we look at part D. Total initial of +13, total final of +13. So that is our answer. Our answer is D. All right. For the last concept questions is, in an elastic collision, is the kinetic energy of each object the same before and after the collision? The The answer is no. It may change. One of the definitions of an elastic collision is the total kinetic energy needs to stay the same. But the question says each. Each of the object's kinetic energy can change. One object can gain kinetic energy, and another object can lose kinetic energy, but the total kinetic energy must stay the same. So in an elastic collision, is the kinetic energy of each object the same before and after the collision? The answer is it could be, but it doesn't have to be. And that's it.